Welcome to the Deep Dive. We're your shortcut to getting truly informed.
And today we are diving laser-focused into Chapter 6, Ecology, Population Dynamics.
That's right. Specifically, the high-yield stuff you absolutely need for those multiple-choice questions. No fluff.
Exactly. We're hitting the key definitions, the core concepts, and maybe a few surprising facts to make it all stick. The goal, speed, depth, and getting you prepped.
Okay, let's do it. We're talking life strategies, population controls, how species spread out, and even how pure chance shapes evolution. First up, R versus K selection, a fundamental divide.
Right. So R and K selection, it's basically a spectrum describing how organisms spend their energy budget.
Energy budget, you mean like for reproduction versus survival?
Precisely. Do you invest a ton of energy into raising just a few offspring, making sure they survive, or do you just, flood the environment with sheer numbers?
Got it. So K selected are the first type, and heavy investors.
Yeah, K selected. Think high energy per offspring, lots of parental care. The result is generally higher survivorship for the young.
Quality over quantity.
You got it. It's like they expect their young to make it.
Like humans, right? Or lions, elephants, whales. If a young human dies, it's genuinely shocking. It goes against that K-selected expectation.
Exactly. We put so much into each one. Now, flip that coin, you get R-selected species.
The quantity players.
Totally. They pour energy into rapid reproduction, make tons of offspring, but offer pretty much zero parental care. Survival. That's mostly luck of the draw.
So high mortality for the young is just expected.
Oh, absolutely. Think shellfish just releasing clouds of eggs and sperm into the water. Or those poppy seeds you see everywhere, piney black dots.
Yeah, thousands on a single flower head sometimes.
Yeah.
Minimal investment in each seed.
Exactly. And a key feature for R-selected species, especially the invasive ones, is that super short generation time.
That makes sense for invasive species, like rats or zebra mussels.
Perfect examples. They can reproduce so fast they just overwhelm native species or any control efforts. Speed is their weapon.
It's a numbers game. So K is like careful cultivation, R is like a scattergun approach.
That's a good way to put it. Now think about vulnerability. If you're K-selected, often quite specialized, does that high investment make you fragile if things change?
Yeah, maybe. If your specific niche disappears and you reproduce slowly.
Right. You can't adapt quickly. The R-selected species with their fast turnover might bounce back quicker from disturbances. Less invested, maybe more adaptable in some ways.
Interesting trade-off. What about things that don't fit neatly? You mentioned the oak tree before.
Ah, the oak tree. Great example of the spectrum idea. The acorn itself is pretty big, right? Lots of stored energy. That feels K-selected.
Sure, compared to a poppy seed, definitely.
But then, an oak produces thousands of acorns over its life. Most just feed squirrels or rot. That massive quantity feels very R-selected.
So it's kind of both.
It shows that R and K aren't strict boxes. They're endpoints on a continuum. Nature's messy like that.
Okay, so this R versus K thing, it maps directly onto survivorship curves.
Yeah.
Those graphs showing survival odds over a lifetime.
Absolutely directly. The curves just visualize the life strategy. Let's start with type Y.
It sounds like the K-selected pattern.
It is. High survival through early and middle life. Most individuals live to old age, and then mortality kicks in. The graph stays high, then drops off sharply at the end.
So humans again. Whales, elephants, things you don't really expect to die young from random causes.
Exactly. You expect them to get old. Now, swing completely the other way. Type 3.
That must be the R-selected guys.
Yep. Huge die-off right at the beginning, extremely low survivorship for the very young. The graph plummets immediately.
Like those shellfish eggs or fish larvae.
Perfect. Millions are produced, maybe only dozens survive that initial phase, but if you do make it past that early slaughter,
then your chances are actually pretty good.
Much better, yeah. The curve flattens out for those lucky few survivors.
Okay, high early survival, type 1, massive early die-off, type 3. What's in the middle? Type 2. That one seems less intuitive.
Type 2 represents a constant probability of dying throughout life. It's more or less a straight diagonal line sloping downwards.
Constant risk. What kind of animals fit that?
Think about things like ducks or rabbits, maybe some lizards or songbirds.
Okay. Why them?
Well, they might put some energy into parental care, maybe more than a pure R strategist.
A bit K-ish.
A bit, yeah. But they're also constantly vulnerable to predators, mostly. A hawk doesn't care if a rabbit is 1 year old or 5 years old. It's just lunch.
Ah, I see. So the risk of getting eaten by a fox or a hawk is pretty consistent throughout their whole life.
Right. There isn't really a safe period once they're out on their own. If you picture an animal that's always kind of looking over its shoulder for danger, that's often a type 2 survivorship.
Got it. So it really shows the different evolutionary bets organisms make.
Mhm.
Bet on surviving youth, bet on overwhelming numbers, or just deal with constant risk.
Okay, shifting gears a bit.
Yeah.
From life history to where organisms actually live,
Ah.
how are populations distributed in space? There are three main patterns.
And the most common is clumped, right?
By far the most common. Individuals gather together in patches.
Why? Usually around resources.
Almost always. Water holes in a desert, fertile soil patches for plants, maybe good nesting sites. Or for humans, jobs, cities, infrastructure.
We are definitely a clumped species. We need resources, and frankly, we seem to need each other.
That social aspect is key for humans, yeah. Our clumping is driven by resources and cooperation.
It's interesting how our clumping, like building cities or farms, can then force other species into smaller clumps in remaining habitats, like parks.
That's a huge impact. Okay, second pattern, uniform distribution, evenly spaced out.
This one seems less common. What causes it?
Usually direct interactions between individuals. Think territoriality.
Ah, like mountain lions with their huge separate ranges, or those seabirds on cliffs.
Exactly. Those nesting seabirds actively defend their space, teching neighbors who get too close. Maintaining that personal space that's often smarter animals that frankly don't like each other too close.
Keeping their distance. Okay, so clumped, uniform. What's the last one?
Random distribution. Individuals are spaced unpredictably. No real pattern.
And this is the rarest.
Yeah, pretty rare in nature. It tends to happen only when two things are true. Resources are abundant and evenly spread, and the organisms don't strongly attract or repel each other.
So maybe like some plants, where seeds just land and grow if there's enough water everywhere, and they don't have brains to be territorial.
Pretty much. Think dandelions in a consistently moist field. But since perfectly uniform, abundant resources are uncommon, so is random distribution.
Okay, so we know how they spread out, but what stops populations from just growing infinitely? Limiting factors, right? And this density dependence thing.
Right. We split limiting factors into two types based on density. First, density-dependent factors.
Meaning their effect changes depending on how crowded the population is.
Exactly. The impact gets worse as the population density N increases. Usually it involves running out of something.
Like food, water,
Yeah.
space.
All classics. Think about plants competing for sunlight and root space in a thick forest. Or wildebeest at a shrinking water hole. If there are only a few, they might be fine. If there are thousands.
They drink it dry much faster, and the death rate skyrockets.
Precisely. And remember, animals generally don't ration. They consume until it's gone. The limitation depends directly on how many are consuming.
Okay, so what's the other type?
Density-independent factors. These kill organisms regardless of population density.
Like a natural disaster.
Yeah, usually big abiotic events. A sudden freeze that kills all the fish in a pond, whether there were 10 or 10,000. A volcanic eruption. A severe drought affecting everyone equally. A massive dust storm.
The event's impact isn't related to how crowded things were.
Correct. It just wipes things out indiscriminately.
And all these factors together determine the ultimate limit,
Yeah,
the carrying capacity.
exactly. Carrying capacity, which we symbolize with a capital K, is the maximum population size and that a particular environment can sustain over the long term, given the available resources and those limiting factors.
And it's crucial to remember, K is the limit, N is the actual population number at any given time.
Yes, gotta keep K and N straight. K is the ceiling, N is where you are relative to it.
So we've talked about N, the population size, and K, the limit. But something interesting happens when N gets really, really small, right?
Yeah.
Evolution starts working differently, not just selection.
That's right. When populations are small and isolated, random chance plays a much bigger role in shaping their genetic makeup. This is the realm of genetic drift.
Genetic drift, so random changes in gene frequency.
Exactly. It's about random fluctuations in the proportions of different alleles or gene versions in the gene pool. It happens when, purely by chance, some individuals leave behind more descendants and genes than others.
And this is strongest in small populations.
Crucially important. Imagine a landslide hits a small valley with, say, 50 frogs, 25 red, and 25 green. If the landslide randomly kills 15 red ones and only 5 green ones,
Then the surviving population is now skewed towards green frogs, just by dumb luck. Not because green was better.
precisely. It wasn't selection for greenness, it was just random mortality disproportionately hitting red. For drift to be significant, you need that small population size and a random event.
Okay. And there are specific types of drift to know, like the bottleneck effect.
Yes, the bottleneck effect is a classic. The name is pretty descriptive. It's when a population undergoes a drastic, severe reduction in size.
Like from a catastrophe. Or maybe overhunting.
Both are common causes. A huge fire, a disease, or humans hunting a species almost to extinction. The few survivors that make it through the bottleneck are unlikely to represent the full genetic diversity of the original population.
So the new population that grows from those survivors is genetically impoverished.
Often, yes. Think of the northern elephant seals, hunted down to maybe just 20 or 30 individuals. Now there are thousands again.
But they're all super related.
Highly genetically similar. They lost a huge amount of variation during that bottleneck. Makes them potentially vulnerable to future threats, like a new disease. That lack of diversity is the bottleneck's lasting signature.
Wow. Okay, what's the other main type? Founder effect.
The founder effect. This is basically genetic drift that happens when a new population is established by a very small number of individuals, the founders.
Breaking away from a larger source population.
Yeah.
Like colonizing an island.
Exactly. A few birds get blown off course to a remote island. A few seeds float across the ocean on a log. Those founders are, by definition, a small, random sample of the original group.
So they might carry rare genes at a higher frequency just by chance, or maybe lack common genes from the mainland.
Both can happen. Their gene pool might look quite different from the source population simply because of who happened to do the founding. Think Galapagos finches or the Channel Island foxes off California. They started from small, likely non-representative founding groups.
So bottleneck is about surviving a crash. Founder effect is about starting somewhere new with just a few individuals. Both lead to reduced, possibly skewed genetic diversity due to chance.
You got it. And that isolation, the geographic separation involved in the founder effect, or maybe splitting a population with a new mountain range or river?
That leads to speciation, making new species.
It's the key ingredient for the most common type, allopatric speciation.
Allopatric, meaning different homeland.
Right. A physical barrier splits a population. The two isolated groups then evolve independently. They face different selective pressures, experience different random drift weights,
And eventually they become so different.
that they can no longer successfully interbreed, even if they came back together. At that point, boom, you have two distinct species where you once had one, driven by that initial geographic separation. #outro.
Okay, that was a serious deep dive. R versus K strategies, the survivorship curves they create, how populations distribute themselves, clumped, uniform, random, and what limits them, especially density dependence.
And finishing with how chance, through genetic drift, bottlenecks, and founder effects, really messes with small populations and can even drive the formation of new species through allopatric speciation.
Definitely lock down those definitions and the key examples, the whales, the poppies, the oaks, the elephant seals, that's where the points are.
And think about us, humans. We're case-selected, right? High investment, long lives. Yet our population N grows incredibly fast, pushing limits, and we love to clump.
That clumping. You think that's part of our success, cooperating in groups?
Many believe so. Our intense social clumping might be why we became the special species driving cooperation and intelligence, but there's a flip side.
Which is?
Our success in clumping and growing means we concentrate our resource use. We create intense local density-dependent pressures, not just for us, but drastically reducing the carrying capacity K for countless other species around us.
So our own evolutionary strategy, our clumping behavior,
Yeah.
directly impacts the ecological ceiling for everything else.
It's a profound connection, so here's something to chew on. How does that deep-seated human drive for group belonging, our inherent tribalism and social clumping, not only shape our societies, but continuously exert pressure on global resources, effectively lowering the carrying capacity for life across the planet?